Question 5. This question is about element X, which forms trifluorides, pentafluorides, and trisodium X. Atom X is phosphorus, as it can form all three of the molecules. First molecule we'll look at is trisodium phosphide. This is where phosphorus ions bond with sodium ions to form the molecule. So sodium ions form by sodium atom, here with one electron, losing that electron to form the 1+ ion. And this happens to all three of the sodium. And the opposite happens to phosphorus. Instead of losing electrons, it gains 3 electrons. And these 3 electrons are the ones lost by the 3 individual sodium atoms. So here we have the 5 valence electrons in the phosphorus outer shell, gaining 3 electrons, making the phosphorus 3- ion. And these both now have full outer shells, so they have more stability and it's just better for both of them. And here we can see the overall bonding, the overall ionic bond. So we've got 1, 2, 3 sodium and 1, 3- phosphorus ions to give a charge of neutral or 0. And this is known as ionic bonding because we've got metal ions here and the non-metal ion here. The next two structures are phosphorus trifluoride and phosphorus pentafluoride. So here we've got the Lewis structures. We've got phosphorus pentafluoride here, crudely drawn in paint, and phosphorus pentafluoride here. So phosphorus trifluoride obeys the octet rule. We've got a lone pair here and 3 bonds, 1, 2, 3, and this gives us 8 electrons in the outer shell, so the full octet. But over here we can see we've got 1, 2, 3, 4, 5 bonding pairs, which breaks the octet rule, giving us 10 electrons in the outer shell. However, phosphorus can do this as it's a hypervalent species, which will be discussed later on in the movie. So the bit that's just popped out here is a way of explaining the bonding in phosphorus pentafluoride without breaking the octet rule. So we'll pop this diagram here. Just by having a quick look, we can see we've got 4 bonds around phosphorus, 8 electrons around fluorine down here, the fluoride ion. Perfect. They can bond. We've got the electrons have been transferred, one from phosphorus, one of its valence electrons, onto the fluorine, which is why it now has 8. And the 4 valence electrons left have all been shared with fluorine atoms, and fluorine has shared 1 electron with phosphorus, giving it 8 electrons or 4 bonding pairs. This structure also has different resonance forms. So this fluoride minus, this could be here, 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 or here, but the phosphorus in the middle will always have the positive charge, and this will always lose electron in the charge separation idea. This next slide is about molecular shapes and the electronic geometries of those molecules. So different molecular shapes occur due to different numbers of bonding and lone pairs of electrons. This is because electrons are negative and they want to maximize their distance apart. For example, phosphorus trifluoride has a tetrahedral electronic geometry because we've got 4 electron groups. So I'll just highlight them. We've got the bonding pair, the first one, the second bonding pair, third bonding pair, and a lone pair here. However, this is not its molecular shape. It has a molecular shape that is pyramidal, trigonal pyramidal, and this is because the lone pair is a lot more repulsive than the bonded electrons. Firstly, this is because it's not shared between 2 atoms, and it is just closer to the phosphorus, and it can just whiz around. It's got a larger space when it's around the phosphorus atom, and this causes the molecule to have angles of 107 degrees. So all these angles here are 107 degrees. So phosphorus pentafluoride has got the trigonal bipyramidal shape in both the electronic geometry, because you've got 5 electron groups, and in the shape, because you've got 5, again, bonded pairs. So this leads to 2 different bond angles. We've got 90 degrees. So if we look at this molecule, we've got the axial going straight through. This molecule is sometimes called a seesaw, because if you imagine you like balance it out here, it moves back and forth. But we've got the axial going straight through, and we've got the equatorial. So this is like a trigonal plane, so this has 120 degrees here, but between the axial and the plane, the trigonal plane, got 90-degree bond angle. This next slide is about hybridization. I'm going to talk about phosphorus trifluoride first. So phosphorus can form phosphorus trifluoride easily. This is because it can form sp3 hybrid molecules. Just pop these 2 bits up. we can see that the 2s orbital can combine with the 2px, or the 2py, or with the 2pz to give these 4 orbitals here in the tetrahedral electronic geometry. So these could be bonding or lone pairs, whatever, but in our molecule, we've got 3 bonding and 1 lone pair. So that gives us the trigonal pyramidal shape. So if we look at this diagram here, so this is the energy diagram of the orbital, so our 3s orbital here, and our 3p orbitals here. So the energy of these 4 orbitals is exactly the same as these 4 orbitals. So it's just kind of like an average energy if we added all of these up together. So all the electrons in black, they're all from the phosphorus atom, and they're all the valence electrons. So if we've got 4 molecular orbitals, atomic orbitals, here, we're going to have the 4 molecular orbitals. And these empty, half-filled empty orbitals, this is where a fluorine electron, can come, and they can share this orbital and form a bond. And if fluorine shares this black electron here, it's going to complete this octet. And if these 3 orbitals here get 3 fluorine atoms, we're going to complete the phosphorus octet. So if I pop the fluorine atoms in, we got the blue ones here, show they're different. That completes the phosphorus octet, and the fluorine octet's also now complete. Now we're going to talk about the hybridization of phosphorus pentafluoride. So this is obviously a little bit different because we know this molecule breaks the octet rule because it's got 10 electrons around the central phosphorus atom. However, this can be explained with the idea of hybridization. So instead of 4 atomic orbitals this time, these 4 that we had before, we've now got this extra one, the 3dz squared. So 3s, 3px, 3py, 3pz, and the 3dz squared. 5 molecular atomic orbitals to give these 5 hybrid orbitals, the sds. So we've got a little diagram here, another energy diagram that I had before. However, we've got a little bit different this time. We've added in these 3d orbitals. So normally in phosphorus, this orbital is unoccupied, but since this gap in energy between 3p and 3d is so small, we can actually promote electrons from below to up into this orbital. So 1 electron. So we've got atomic orbitals, and they can combine to give us the 5 sp3d hybrid orbitals. And it's the same idea as before. We can put the fluorine electrons in, but this time instead of having 3 half-filled orbitals, we've got 5. So that means we can complete the octets of 5 fluorine atoms. And that in turn means the phosphorus, does not have a complete octet. Because if it did, we'd not have this one here. No. These 4 orbitals here. So that's how it has the 5 bonds around it. And yeah, this bit down here is just about the d orbital being close in energy. So one of the final bits of the question is about element Y. So element Y can form trifluorides, but not pentafluorides. So we're going to explore that a bit here. So element Y, nitrogen trifluoride forms exactly the same as phosphorus trifluoride. So we've got the sp3 hybrid orbitals, 3 of them half-filled, share electrons, blah blah blah. We're not going to talk about that anymore. So now nitrogen, it can't form nitrogen pentafluorides. So why is this? So compared to phosphorus, it's relatively small. So we've got an atomic radius of 74 nanometers, whereas phosphorus has an atomic radius of 110 nanometers. So this is a bit bigger, a bit exaggerated, but it gets the point across that it's really big, it can form bonds, but nitrogen can't. And it's also the fact that the electron groups would be so close together, the repulsion would be incredibly large, and it just wouldn't be a viable structure. However, there's another reason it can't be formed. So if we look at this energy diagram, so for the nitrogen trifluoride, we got this little bit down here, we got sp3 hybrids, it's all nice, all checks out, whatever. But when we try and make the pentafluoride, like we did with phosphorus, the 3d orbital, this is way too big. So if this was 3d or 3p orbital, 3s, this orbital here would be able to come across, we'd make sp3d hybrids, it'd be fine, but this is way too big. So we can't have that. We're just going to stick with sp3 hybrid orbitals and the trifluoride, nitrogen trifluoride. This last slide is about the bond length of phosphorus pentafluoride. So due to its bipyramidal structure, as you can see here, it's got two different bond lengths. So the bond length across here is 2.04 angstroms, but the axial bond length is 2.19 angstroms. This is because they face different amounts of repulsion. So the equatorial faces repulsion at 90 degrees, both of the axial bonds, and at 120 degrees from two of the other equatorial bonds. However, the axial bond actually faces more repulsion, as you've got repulsion 180 degrees from the other axial bond, and at 90 degrees from the other trigonal planar bonds, the equatorial ones. So this means that this bond slightly lengthens to decrease the repulsive force.